What is hidden under the ice of Antarctica? 13 secrets and wonders of Lake Vostok. Think Antarctica as nothing more than an endless white desert? A place so cold and empty that nothing could possibly live there? Throw out those old schoolbook maps and simplified documentaries right now. Beneath 4 kilometers of solid ice hides one of the most astonishing natural laboratories our planet has ever created. Today, I'm going to walk you through 13 carefully documented discoveries that still leave even veteran polar researchers quietly stunned. Stay with me until the very last line. By the end, you'll understand how this buried lake quietly maintains liquid water for millions of years, supports microscopic life in complete darkness, and offers us one of the clearest windows into what alien oceans on distant moons might really be like. Kicks off our list, the sheer size that makes every other lake on Earth feel small. Imagine you're standing on the surface of East Antarctica, wind howling across the endless plateau, temperature hovering around -55 Celsius. Beneath your boots, hidden under an ice sheet that would dwarf most mountain ranges, lies a body of water so large it completely redefines our sense of scale. Lake Vostok stretches roughly 250 kilometers from one end to the other. That's longer than the distance from New York City to Philadelphia. At its widest point, it reaches about 50 kilometers across, roughly the width of Rhode Island. And the volume? More than 5,400 cubic kilometers of liquid water. To put that number into something you can actually picture, consider this. The lake contains enough water to fill every single swimming pool in the United States more than 300,000 times over. If you somehow drained it completely and spread the water evenly across the continental United States, the entire country would be covered by a shallow layer almost 2 meters deep. That single fact alone should make you pause. Most people think of Antarctica as a dry, frozen continent. Yet right here, locked away, is a freshwater reservoir bigger than many of the Great Lakes combined. How do scientists even know the shape and size so precisely? Decades of airborne radar surveys, satellite laser altimetry from missions like Cryosat, and ground-based seismic profiles have slowly painted the picture. Starting in the early 1990s, Russian, British, and American teams flew grid patterns over the ice, sending radio waves downward. Wherever those waves bounced off a sharp change from ice to liquid, they recorded a strong echo. By the early 2000s, the outlines were clear. Later missions refined the edges, measured the depth at different points, and confirmed the lakebed slopes gently from about 400 meters below sea level at one end to more than 800 meters at the other. Now picture what that actually looks like if you could magically remove the ice cap. You would see a long, narrow basin cradled between 2 ancient ridges of bedrock. The water surface, because yes, it has a true surface even under 4 kilometers of ice, sits roughly 500 meters below present sea level in most places. Sunlight has never touched it. No rivers flow in or out in the conventional sense. The only exchange happens through extremely slow melting and refreezing at the ice-water interface. That interface itself is fascinating. The bottom of the ice sheet is not flat. It bulges slightly downward over the lake because the pressure from above is partially balanced by the buoyancy of the liquid below. Scientists sometimes compare the lake to a giant pressurized thermos. The enormous weight of the overlying ice, roughly 4,000 meters thick in this region, creates hydrostatic pressure at the bottom, around 345 times greater than the pressure we feel at sea level. That pressure lowers the freezing point of water just enough to keep it liquid, even though the temperature hovers around -3 degrees Celsius. Without that pressure, the entire volume would be solid ice. With it, the water remains fluid, circulating in extremely slow, density-driven currents that have probably been turning over for millions of years. The isolation is almost perfect. Core samples taken from the ice directly above the lake show that atmospheric gases trapped in bubbles change dramatically once you cross into the accretion ice, the layer that freezes onto the bottom of the ice sheet from the lake water itself. Above that boundary, you find normal air composition from thousands of years ago. Below it, the gas mix is radically different, enriched with gases that could only come from deep, long-trapped water. That sharp transition is one of the cleanest proofs we have that very little mixing has occurred with the outside world for an extraordinarily long time. And here comes the part that still gives researchers a quiet thrill. Because the lake is so massive and so well sealed, it acts like a planetary-scale pressure cooker that has been running steadily since long before our species existed. Every cubic meter of water inside has been subjected to the same immense forces, the same near-constant cold, the same complete darkness for epoch after epoch. That stability creates conditions almost impossible to replicate in any laboratory on the surface. Whatever chemistry or biology has unfolded down there has done so in near-perfect isolation, free from the rapid changes, oxygen spikes, temperature swings, meteor impacts that have reshaped the rest of the biosphere again and again. To give you one last sense of scale before we move on, if you could somehow place Lake Vostok on the surface of Mars, its footprint would cover an area larger than many of that planet's famous impact basins. Yet here on Earth, we have been walking over it for decades without realizing just how much liquid was waiting below. It forces us to rethink what frozen continent really means. Antarctica is not merely covered in ice, it cradles hidden seas. We have just measured the giant that hides in plain sight. But size alone is only the beginning. What happens when a lake this enormous is cut off from the rest of the planet for tens of millions of years? That question takes us straight to the next wonder. We have just measured the giant that hides in plain sight, but size alone is only the beginning. What happens when a lake this enormous is cut off from the rest of the planet for tens of millions of years? That question takes us straight to the next wonder. Claiming second place, a perfect time capsule sealed longer than most of human history can even imagine. Picture this: layers upon layers of snow falling quietly over East Antarctica, each winter adding another thin page to an endless book. Year after year, century after century, those flakes compress into solid ice, trapping tiny bubbles of ancient air, like messages in bottles. The ice sheet keeps growing thicker, pushing downward with relentless weight. Eventually, the bottom starts to melt, just enough from geothermal heat rising from the planet's interior, and that meltwater collects in the deepest depressions of the bedrock. Over time, the water gathers into a lake, and then the ice above keeps advancing, eventually covering everything in a blanket so thick that no sunlight, no wind, no fresh rain or dust from the outside world can ever reach it again. That covering moment happened somewhere between 15 and 25 million years ago, according to the best current estimates from ice core studies, radar mapping, and models of Antarctic glaciation. Scientists piece this together by looking at when the East Antarctic ice sheet stabilized into its modern, cold-based form after a warmer period in the Miocene. Before that, the region experienced wetter, more fluctuating conditions, with ice advances and retreats. Once the thick, stable ice cap locked in place, exchange with the atmosphere effectively stopped. The lake became a closed system, its water circulating only through extremely slow processes of basal melting at one end and refreezing at the other as the ice sheet slowly slides across the basin. To give you a sense of just how long that is, consider this. 15 million years ago, our planet looked dramatically different. Early ancestors of modern elephants and horses were just appearing in Africa. Grasslands were spreading, replacing forests in many places. The Himalayas were still rising rapidly from the collision of continents. Human-like primates would not walk upright for another 13 million years or so. The lake has been hidden through all of that, through the entire rise and diversification of mammals, through massive shifts in ocean currents, through the formation of the Isthmus of Panama that changed global climate patterns forever. While the world above transformed repeatedly, the water below remained untouched, preserving whatever chemistry and biology was present when the seal formed. How do researchers arrive at such an enormous number with any confidence? They rely on several independent lines of evidence. First, Paleoclimate records from deep ice cores drilled nearby show when the Antarctic continent became permanently glaciated on a large scale, around 34 million years ago at the Eocene-Oligocene boundary, with full East Antarctic stability coming later. Second, the accretion ice, that bottom layer where lake water freezes onto the underside of the glacier, contains chemical signatures that match no modern surface water. Gas concentrations, especially helium from radioactive decay in bedrock, build up in ways that only make sense over millions of years without escape to the atmosphere. Third, modeling the ice flow dynamics across the lake basin shows the glacier has been overriding it continuously for at least 15 million years, without major disruptions that would allow mixing. Imagine standing at the ice lake interface, if you could somehow be there. The water is dark, almost black in the complete absence of light. Pressure squeezes everything, about 350 atmospheres, enough to make the water behave in ways we rarely see at the surface. Temperature hovers right around -3 degrees Celsius, cold enough to freeze ordinary water instantly, yet the pressure depresses the freezing point just enough to keep it liquid. No waves crash, no fish swim, no plants photosynthesize. Only the very faint, slow creep of the ice sheet overhead disturbs the silence, perhaps once every few thousand years, causing a subtle shift in currents. It is the quietest place on Earth, a realm where time itself seems stretched out. Yet that long isolation creates something remarkable, a natural experiment running for eons. Any organisms that were trapped when the lake sealed off, or that might have entered through ancient groundwater connections before the final lockdown, have had to adapt or perish in near constant conditions. Nutrients are scarce, delivered only by tiny amounts of dissolved minerals from bedrock or organic traces from the melting glacial ice. Energy sources are limited to chemical reactions, perhaps oxidation of trace metals or hydrogen from deep geological processes. No sunlight means no photosynthesis as we know it. Evolution here, if it occurs at all, proceeds at an extraordinarily slow pace compared to the surface world, where rapid environmental changes drive adaptation. Scientists sometimes describe Lake Vostok as one of the planet's most pristine archives. The overlying ice preserves a detailed climate record going back more than 400,000 years. Temperature swings, greenhouse gas levels, volcanic eruptions captured in ash layers. But the lake water itself may hold an even older story, frozen in time. Accretion ice samples pulled from the bottom of drill cores show microbial DNA fragments and chemical clues that hint at life forms adapted to extreme oligotrophy, ultra-low nutrient conditions. Whether those microbes are truly indigenous to the lake or contaminants from drilling remains carefully debated. But the possibility alone excites researchers studying how life might persist in isolated, energy-poor habitats. Think about the contrast for a moment. On the surface, we measure time in days, years, lifetimes. Down there, 15 to 25 million years is just one long, unbroken moment. Nothing rushes. Nothing invades. The lake sits like a patient observer of Earth's wild history, recording nothing but its own quiet endurance. It reminds us how vast geological time really is, how small our own chapter appears against that backdrop, and how much we still have to learn about the resilience of even the simplest forms of life. We have uncovered a sealed world older than mountains in many places. But a perfect seal means nothing escapes and nothing enters. What kind of chemistry builds up when oxygen and other gases have nowhere to go for millions of years? That revelation waits just ahead. We have uncovered a sealed world older than mountains in many places. But a perfect seal means nothing escapes and nothing enters. What kind of chemistry builds up when oxygen and other gases have nowhere to go for millions of years? That revelation waits just ahead. Building to third place, the hidden rhythm that moves in total darkness, without a single ray of sunlight ever reaching it. Imagine you are floating weightless in the middle of this buried lake. No light penetrates from above. The water is perfectly still, or at least it seems that way at first glance. Then you feel it. A very slow, very gentle rise and fall. Almost imperceptible, repeating roughly twice a day. The entire water column lifts a little, then settles back down. Not waves crashing like you know them from the ocean. Not even ripples you could see with your eyes. Just a subtle, pulsing heave that affects every cubic meter of liquid from surface to bottom. That pulse is caused by the moon and the sun pulling on the Earth, the same gravitational force that creates ocean tides twice a day everywhere else on the planet. Even though Lake Vostok sits under 4 kilometers of ice, the solid ice sheet above it is not rigid enough to completely cancel out those gravitational tugs. The ice actually flexes ever so slightly, about 12 to 15 millimeters up and down over the lake basin, and that tiny deformation is transmitted straight through to the water. The lake responds by rising and falling in sync with the lunar and solar cycles, just like any open sea would. To give you a sense of scale, 12 millimeters may sound trivial, less than half an inch. But when you multiply that vertical movement across a surface area of roughly 12,500 square kilometers, the total volume of water being displaced becomes enormous. Every tidal cycle moves hundreds of thousands of cubic meters of water up and down inside the sealed basin. That is not turbulence or mixing in the chaotic sense. It is an orderly, predictable oscillation that scientists have measured with sensitive tilt meters and seismometers placed on the ice surface directly above the lake. How do we know this happens at all? The first strong evidence came from long-term GPS stations installed on the ice sheet in the early 2000s. Those instruments recorded periodic vertical motions that matched predicted tidal amplitudes for the region. Later, airborne and satellite radar data helped confirm that the ice flexes more over the lake than over the surrounding bedrock, because the liquid underneath provides less resistance than solid rock would. By the middle of the last decade, dedicated seismic arrays picked up very low-frequency signals, microseisms, that lined up perfectly with the twice-daily tidal forcing. All of these independent measurements point to the same conclusion. The lake breathes, very slowly, in rhythm with the rest of the planet. Now picture what that movement actually does inside the water. Because the basin is long and narrow, the tidal deformation is not uniform. Near the center, the rise is greatest. Closer to the edges, it is smaller. That difference creates extremely gentle pressure gradients, tiny horizontal flows that circulate water along the length of the lake at speeds measured in millimeters per second or even less. Over thousands of years, these sluggish currents can redistribute dissolved chemicals, nutrients, and perhaps even microbial cells from one part of the lake to another. It is the slowest conveyor belt imaginable, yet it never stops. The really intriguing part is how stable this rhythm has remained. The ice sheet above has been sliding across the lake at roughly 2 to 3 centimeters per year for millions of years. That slow creep should, in theory, gradually change the geometry of the basin and alter the way tides are transmitted. Yet the tidal signal we measure today is remarkably consistent with models based on the current lake shape. That consistency suggests the ice lake system has reached a kind of dynamic equilibrium. The glacier adjusts just enough to keep transmitting the tidal force without major disruption. Scientists sometimes compare this tidal behavior to a planet-sized heartbeat. The moon and sun are pulling on Earth's entire mass, and even a deeply buried pocket of water feels that pull and answers with its own quiet rise and fall. It is a beautiful reminder that no part of our planet is truly isolated from the rest of the solar system. Gravity does not care about 4 kilometers of ice. It reaches through and sets the water in motion anyway. Think about the contrast again. On the surface, we see dramatic tides. Boats lifted high, beaches exposed at low water, entire coastlines reshaped twice a day. Down in Lake Vostok, the same fundamental force operates, but in near absolute silence and darkness. No seabirds wheel overhead. No crabs scuttle along the bottom. Just water, pressure, and a patient, repeating cycle that has probably been going on since long before the first humans looked up at the moon and wondered why the sea moved. This rhythmic motion is one of the few connections the lake still has to the outside world. Not through light, not through air, not through flowing rivers, but through the invisible thread of gravity. It is a subtle but powerful link that keeps the system from being completely static. And because the tides exist, they create tiny variations in pressure and temperature that could, over geological time, influence where and how any chemistry or biology might concentrate. We have listened to the faint heartbeat of a lake that no one will ever swim in. But that gentle pulse is only part of the story. Beneath the calm oscillation, something far more extreme keeps the water from turning to solid ice. That secret is coming up next. We have listened to the faint heartbeat of a lake that no one will ever swim in. But that gentle pulse is only part of the story. Beneath the calm oscillation, something far more extreme keeps the water from turning to solid ice. That secret is coming up next. Sliding into fourth place, the quiet defiance that stops an entire lake from freezing solid when everything says it should. Picture yourself descending through the ice sheet, kilometer after kilometer of compressed snow turning to crystal clear ice. Pressure building until your ears would pop if you could actually be there. At last you reach the bottom interface, 4,000 meters down, and suddenly the solid floor gives way to dark, liquid water. The temperature reads -3 degrees Celsius. On the surface, that would mean instant freezing. Lakes and rivers lock up solid long before they reach zero. Yet here, the water refuses to turn into ice. It stays fluid, circulating in its slow, tidal dance. Even though the cold is deep enough to preserve mammoths in Siberia for tens of thousands of years. The reason is pressure. Immense, unrelenting pressure from the weight of the ice overhead. Every square centimeter at the lake bottom feels the force of roughly 345 atmospheres pushing down. That is the same pressure you would experience if you dove to about 3,400 meters in the open ocean, deeper than most submarines are designed to go. Under that squeeze, the freezing point of pure water drops. Not by a fraction of a degree, but by several full degrees. At 345 bars, the freezing point falls to around -3.2 degrees Celsius. Since the actual water temperature hovers right around -3 degrees, it sits just above the point where it would solidify. The lake is literally being held liquid by the crushing weight above it. To make this clear, think of what happens when you open a can of soda that has been in the freezer too long. The liquid inside is below 0 Celsius, but the pressure from the carbon dioxide keeps it from freezing until you crack the seal and release the pressure. Then it turns to slush almost instantly. Lake Vostok works on a similar principle, except the can is the entire ice sheet, and the pressure never gets released. As long as the ice remains thick enough, the freezing point stays depressed, and the water stays liquid. Scientists first predicted this effect back in the 1960s, when early radar flights detected strong reflections from beneath the ice, signals that could only come from a sharp boundary between solid ice and liquid water. Later thermodynamic models, refined with data from ice cores and direct pressure measurements in deep boreholes elsewhere on the continent, confirmed the numbers. The phase diagram for water shows the freezing line sloping downward with increasing pressure until you reach very high values where exotic ice phases appear. In the range found at Lake Vostok, we stay firmly in the normal liquid region, just barely. Now imagine standing, or rather floating, at that interface. On one side is the underside of the glacier, a smooth, pale blue wall of ice, slowly melting at a rate of perhaps a few millimeters per year in some spots. On the other side stretches the dark water, crystal clear because no sediment or organic particles have entered in millions of years. If you could shine a powerful light downward, you would see the water extending out into blackness, no bottom visible for hundreds of meters in most places. The pressure feels like an invisible hand pressing on every inch of your body, making every breath, if breathing were possible, feel labored and shallow. Yet the water moves freely, responding to those tiny tidal lifts from earlier. This pressure-liquid balance is remarkably delicate on geological timescales. If the ice sheet thins significantly, say due to sustained warming or changes in ice flow, the pressure would drop, and parts of the lake could start to freeze from the bottom up. Conversely, if geothermal heat from below increased, or the ice thickened further, more melting would occur at the base. Right now, the system sits in a narrow, sweet spot, where basal melting exactly balances the very slow freezing that happens as ice flows across the lake and colder surface ice accretes onto the bottom. That equilibrium has held for millions of years, creating one of the most stable, deep environments known on Earth. The implications ripple outward. Because the water remains liquid, dissolved gases, minerals, and any potential organic molecules can stay in solution and circulate instead of being locked into ice crystals. That mobility allows for the possibility of chemical reactions that would be impossible in a fully frozen system. It also means that if microscopic life exists down there, it has access to a dynamic, albeit extremely slow, fluid medium where nutrients can be redistributed and waste products diluted. Researchers often point out that this pressure-driven liquidity is not unique to Lake Vostok. Many subglacial lakes across Antarctica behave the same way. But Vostok stands out because of its size, depth, and isolation. It is the largest and deepest example we have studied in detail, giving us the clearest view of how far pressure can push the boundaries of what we consider normal for liquid water on Earth. Step back for a second and let that sink in. A place colder than your kitchen freezer, buried under ice thicker than many skyscrapers are tall, yet stubbornly refusing to freeze because the planet itself is pressing down hard enough to rewrite the rules of phase changes. It is one of those quiet facts that makes you appreciate how many ways nature finds to keep things in motion, even when everything looks frozen in place. We have seen how pressure cheats the cold and keeps the lake alive as liquid. But when you combine that pressure with millions of years of isolation, another extreme builds up, one that changes the very air dissolved in the water. That overload is next. We have seen how pressure cheats the cold and keeps the lake alive as liquid. But when you combine that pressure with millions of years of isolation, another extreme builds up, one that changes the very air dissolved in the water. That overload is next. Landing in fifth place, the invisible flood of oxygen that turns ordinary water into something almost otherworldly. Imagine sinking slowly into the dark heart of Lake Vostok. No sunlight has ever reached this depth. The water around you is so clear it feels like swimming through glass. Yet if you could somehow take a deep breath here, which of course you could not, your lungs would fill with something far richer than the air you know at sea level. Dissolved oxygen levels in this lake are estimated to be up to 50 times higher than what you find in ordinary freshwater or even in the open ocean at the surface. That is not a small difference. It is a massive, almost unbelievable saturation. At the surface, typical freshwater holds about 8 to 10 milligrams of oxygen per liter when fully aerated. Deep ocean water drops to 2 or 3 milligrams per liter in oxygen minimum zones. Lake Vostok measurements, based on gas analysis of accretion ice and modeling of pressure effects, suggest concentrations reaching 400 to 500 milligrams per liter, or roughly 2.5 liters of pure oxygen gas dissolved in every single kilogram of water. To put that in perspective, if you could somehow extract and release that dissolved gas at surface pressure, a single cubic meter of lake water would bubble out enough oxygen to fill a small bedroom. How does so much oxygen end up trapped down there? The story starts millions of years ago, when the lake first became sealed under the growing ice sheet. Back then, during the final stages of Antarctic glaciation, the water was in contact with the atmosphere for the last time. Air dissolved into it under normal conditions. Then, the ice closed in. As the ice sheet thickened, the enormous pressure squeezed more and more gas into solution. Oxygen, being highly soluble under high pressure, got forced deeper into the liquid phase instead of escaping as bubbles. Over time, with no way for gases to vent back to the atmosphere, the concentration built steadily. But pressure alone does not explain the extreme level. Another key process is happening at the ice-water boundary. As the glacier slowly slides across the lake basin, its base melts very gradually from geothermal heat rising from below and from the friction of ice movement. That meltwater is extremely cold, close to -50 degrees Celsius at the surface, and carries very little dissolved gas because cold water holds less gas than warm water. When that fresh, gas-poor meltwater mixes into the lake at the top of the water column, it dilutes other components, but leaves oxygen relatively concentrated because the original deep water was already supersaturated. Meanwhile, at the far end of the lake, where colder ice flows in, some water freezes back onto the glacier bottom as accretion ice. That freezing process actually expels gases slightly, but because oxygen solubility is so high under pressure, much of it stays behind in the remaining liquid. The result is a stratified system where oxygen levels vary somewhat from top to bottom, but everywhere they remain extraordinarily high compared to any other natural water body we know. Scientists have reconstructed these concentrations using gas measurements from the accretion ice layers, those thin bands of frozen lake water that were pulled up in drill cores. When the ice samples are melted under controlled conditions in laboratories, the released gases are analyzed with precision mass spectrometry. The patterns match thermodynamic models that predict supersaturation under sustained high pressure and low temperature. Now visualize what that means for the water itself. Under normal conditions, water this oxygen-rich would form gas hydrates, cage-like ice structures that trap gas molecules. In fact, models suggest that small amounts of oxygen clathrates may exist in the coldest, deepest parts of the lake, looking like faint, sparkling inclusions suspended in the darkness. If you could shine a light through a sample, you might see tiny, shimmering points where oxygen molecules are locked inside water cages, almost like microscopic diamonds catching non-existent light. This oxygen overload creates conditions that are both beautiful and extreme. On one hand, high oxygen availability could theoretically support more active metabolism if any microorganisms are present. Aerobic respiration is far more energy efficient than anaerobic pathways. On the other hand, such concentrations are toxic to most surface life forms. Many ordinary bacteria and animals suffer oxidative stress when oxygen levels climb too high. It damages cell structures like a slow internal rusting. Yet whatever life, if any, calls this lake home has had millions of years to adapt to exactly this chemistry. The sheer amount of oxygen also means the lake holds one of the planet's largest reservoirs of dissolved gas in a completely isolated setting. If some future change, a major thinning of the ice sheet, or a shift in geothermal flux, were to suddenly reduce pressure, large parts of the lake could degas violently, releasing bubbles that rise through the water column and potentially destabilize the ice above. While that scenario remains hypothetical and extremely unlikely on human timescales, it illustrates how delicately balanced even this hidden world really is. Take a moment to appreciate the paradox. A place buried in eternal cold and darkness is saturated with the very gas we associate with life and fire: oxygen, in quantities that could, under different circumstances, support combustion. It is as if nature decided to pack one of its most remote corners with the breath of life in overwhelming abundance, then locked the door and walked away for 20 million years. We have breathed in, figuratively, the richest oxygen soup on Earth. But that abundance does not sit still. It interacts with the crushing weight we talked about earlier, creating conditions where even the tiniest forms of life must be masters of survival. Those microscopic inhabitants are coming up next. We have breathed in, figuratively, the richest oxygen soup on Earth. But that abundance does not sit still. It interacts with the crushing weight we talked about earlier, creating conditions where even the tiniest forms of life must be masters of survival. Those microscopic inhabitants are coming up next. No, wait. Before we meet the life that might call this place home, we need to confront the force that shapes everything down there. Claiming 6th place, the unrelenting weight that would crush steel beams and turn human bodies into something unrecognizable in seconds. Imagine you are in a specially built submersible, descending through a hypothetical borehole drilled all the way through the ice sheet. The first kilometer feels manageable, just cold darkness. By 2 kilometers, the hull starts to groan softly under the growing pressure. At 3 kilometers, the sound changes to a low, constant creak, like an old wooden ship protesting against heavy seas. Then you break through the ice-water interface at around 4,000 meters below the surface. The depth gauge reads numbers that most people never see outside textbooks. Pressure equivalent to 3,450 meters of seawater column resting directly on top of you. That is 345 times the atmospheric pressure we live under every day. To help you feel that scale, consider what happens to everyday objects under far less force. A standard aluminum soda can collapses inward at about 90 pounds per square inch, roughly 6 atmospheres. A typical submarine designed for 300 meters max depth faces about 30 atmospheres. At the bottom of Lake Vostok, the pressure is more than 10 times higher than the deepest diving military subs are rated for. If you were somehow exposed to it without protection, your body would be compressed instantly. Bones would shatter, lungs would collapse into tiny pockets of air. Every soft tissue would be forced into the smallest possible volume. It is not dramatic explosion. It is quiet, total implosion. Yet the water itself handles this force without complaint. Liquids are nearly incompressible. Water volume decreases by only about 4% even under 4,000 atmospheres. That tiny compression actually helps keep the density high and contributes to the stability of the liquid phase we talked about earlier. The pressure gradient inside the lake is steep, from the top of the water column right under the ice to the deepest point of the basin floor, another 400 to 800 meters down. The pressure increases by another 40 to 80 atmospheres. That gradient drives the slow vertical mixing we see in density currents. Slightly denser, colder water sinking, warmer or less dense parcels rising in their place. Scientists calculate these pressures using straightforward hydrostatic equations combined with precise measurements of ice thickness from satellite radar and ground-penetrating surveys. The Cryosat mission and follow-up airborne campaigns in the 2000s and early 2020s mapped the ice surface elevation down to centimeters. Subtracting that from known bedrock topography gives the exact water depth at every point. Plug those depths into the density profile of cold, high-oxygen water, and the bottom pressure comes out reliably around 345 bars. Independent seismic soundings cross-check the numbers by measuring how sound waves travel faster through compressed liquid than through ice or rock. Now try to picture the scene at the lake floor. The bottom is not flat sand or mud like you might find in a shallow pond. It is ancient bedrock, probably more than 500 million years old, sculpted by earlier glacial advances and retreats before the lake sealed. Rough ridges and shallow depressions, covered in a thin layer of fine sediment that has accumulated at a rate of perhaps 1 millimeter every 1,000 years. No sunlight means no algae mats, no visible plant life. The only color comes from whatever faint bioluminescence might exist if microbes produce it, though so far, no evidence suggests that happens here. Instead, everything is shades of absolute black, broken only by the imaginary glow of your submersible lights, reflecting off perfectly clear water. Under that pressure, even small movements feel weighted. A gentle current of 1 centimeter per second, barely noticeable on the surface, would require significant force to maintain, because viscosity increases slightly with pressure and the cold temperature. Any bubble that formed, say from a localized release of dissolved gas, would be crushed back into solution almost immediately. The same goes for any hypothetical gas hydrate structures. They remain stable only because the pressure and temperature stay within a narrow window. This crushing force is what makes Lake Vostok one of the most extreme, naturally pressurized environments accessible for study without going to the deep ocean floor or drilling into planetary interiors. It shapes every physical process: how heat flows upward from the Earth's crust, how dissolved chemicals diffuse, how any potential microbial cells might move or attach to surfaces. The pressure is not just a number. It is the dominant character in this hidden world, setting the rules that everything else must obey. And here's the part that still surprises people when they really think about it. Human technology has already pierced this pressure barrier once. In 2012, the Russian drilling team reached the lake's surface after more than 2 decades of careful work. They used a special thermal drill followed by a clean sampling system to avoid contaminating the water with surface fluids. The moment the borehole connected, lake water rose up the pipe under its own pressure, proof that the system was still intact and pressurized exactly as models predicted. No catastrophic blowout occurred because the engineers had calculated every safety margin. Samples were collected, sealed, and brought back for analysis under controlled, high-pressure conditions in laboratories. That single connection gave us our first direct taste of what 345 atmospheres really means in practice. The water that came up was cold, clear, and carried the faint metallic tang of ultra-pure, ancient liquid that had never seen daylight. It reminded everyone involved that we are not dealing with an ordinary lake. We are dealing with a high-pressure chamber the size of a small sea, wrapped in ice and time. Take a breath, figuratively again, and let the weight of that sink in. A place where the planet itself presses down so hard that ordinary rules bend, yet the water flows, the tides pulse, the oxygen saturates. It is a reminder of how much raw physical power lies just beneath our feet, hidden under what looks like lifeless white. We have felt the full weight of the ice sheet bearing down. But under that immense load, something remarkable persists. Tiny forms of life that have turned crushing pressure and darkness into a home. Those survivors are next. We have felt the full weight of the ice sheet bearing down. But under that immense load, something remarkable persists. Tiny forms of life that have turned crushing pressure and darkness into a home. Those survivors are next. Settling into 7th place, the quiet, invisible communities that somehow make a living in a world designed to starve anything trying to survive. Picture the deepest, darkest corner of Lake Vostok. No light, temperatures locked near -3 degrees Celsius, pressure equivalent to 3,400 meters of ocean water. Oxygen so abundant it would poison most surface creatures. And nutrients arriving in trickles measured in parts per billion. If you were to scoop up a liter of that water and peer through the most powerful microscope available, you would not see fish, shrimp, or even tiny crustaceans drifting by. Instead, you might catch glimpses of something far smaller and far more resilient. Single-celled organisms drifting or clinging to microscopic surfaces, carrying on metabolism in ways that challenge everything we thought we knew about where life can thrive. Scientists have recovered genetic material from the accretion ice, the thin layers that freeze onto the bottom of the ice sheet from lake water itself, and from filtered samples collected when the borehole first reached the lake in 2012. Sequencing those samples revealed thousands of DNA fragments belonging to bacteria and archaea. One careful study, published in the early 2020s, identified more than 3,500 distinct gene sequences, pointing to a surprisingly diverse microbial community for such an extreme habitat. These are not the usual suspects you find in soil or seawater. Many belong to groups known for living in deep subsurface environments. Hydrogen-oxidizing bacteria, methane producers, sulfate reducers, organisms that do not need sunlight or abundant organic food. How do they survive when energy and nutrients are so scarce? They rely on chemolithotrophy, literally eating rocks for a living. Trace amounts of hydrogen gas, perhaps generated by slow reactions between water and certain minerals in the bedrock, provide a primary energy source. Iron and manganese compounds dissolved from the ancient continental crust offer additional electron donors. On the other side of the equation, The lake's extraordinarily high oxygen levels serve as an abundant electron acceptor, allowing these microbes to extract far more energy from each molecule of food than anaerobic organisms could. It is like running a high-efficiency engine in a fuel-poor desert. Every calorie counts, but the oxygen-rich air makes each one go much farther. To visualize their world, imagine floating among them. The cells are tiny, most less than 1 micrometer across, drifting in water so pure it rivals the cleanest laboratory ultra-pure water. Some attach to fine sediment particles, or to the occasional mineral grain that has fallen from the melting ice ceiling. Others form loose aggregates, perhaps to share scarce resources or protect against oxidative stress. No colorful pigments here, no chlorophyll, no need for light. Their metabolism is slow, generation times measured in weeks or months instead of hours. Yet over millions of years, that slow pace has allowed them to fine-tune enzymes, membrane structures, and repair mechanisms that let them withstand cold, pressure, and oxygen toxicity simultaneously. One particularly intriguing finding is the presence of gene sequences related to antifreeze proteins and cold shock response systems, adaptations seen in organisms from Arctic sea ice and deep permafrost. Another set of genes suggests pathways for dealing with high oxygen, enzymes that neutralize reactive oxygen species before they damage DNA or proteins. These genetic clues paint a picture of life that has been sculpted by the exact conditions found only in subglacial lakes like this one. Whether all the detected sequences come from active living cells or from preserved ancient DNA remains an open question that requires even cleaner sampling in future missions. But the diversity alone is striking. What makes this microbial story even more compelling is the possibility that some of these organisms trace their ancestry back to the surface world before the lake sealed shut 15 to 25 million years ago. Others may have arrived later through groundwater seeps or cracks in the bedrock that existed in earlier, warmer phases of Antarctic history. Either way, they represent a branch of the tree of life that has evolved in near total isolation. Comparing their genomes to surface relatives shows significant differences: unique metabolic tweaks, novel stress response proteins, that hint at how life can diverge when cut off from the rest of the biosphere for geological epochs. Researchers often describe these findings as a glimpse into Earth's deep biosphere, the vast realm of subsurface life that may outweigh all surface biomass combined. Lake Vostok offers one of the purest windows into that realm because of its extreme isolation and lack of human contamination. Every new sequence recovered adds another piece to the puzzle of how far life can push its limits. No light, minimal energy, crushing pressure, toxic oxygen levels, yet still metabolism ticking along. Step back for a moment and consider the scale of that achievement. On the surface, we measure success in growth rates, reproduction, visible activity. Down here, success looks like barely changing for a million years, staying alive, staying functional, waiting out eternity in a pressurized, oxygen-saturated vault. It is the ultimate demonstration of patience and adaptation. These microbes do not conquer their environment, they negotiate with it, accepting terms no surface organism would tolerate. The discovery of such potential inhabitants also carries a quiet philosophical weight. If life can persist in a place this hostile and remote, what does that say about the odds of finding life elsewhere in our solar system? Subglacial lakes on Earth become natural analogs for the oceans hidden beneath the ice shells of moons like Europa and Enceladus. The same physical principles, pressure keeping water liquid, chemosynthetic energy sustaining metabolism, could operate there too. We have met the unseen residents that turn impossibility into routine. But how did humans ever manage to reach into this sealed world without destroying its purity? The story of that daring technological reach and the careful science that followed comes up next. We have met the unseen residents that turn impossibility into routine. But how did humans ever manage to reach into this sealed world without destroying its purity? The story of that daring technological reach and the careful science that followed comes up next. Rising to 8th place, the moment humanity finally touched a lake that had been hidden for 20 million years, and the razor-thin line between discovery and contamination. Picture the scene at Vostok Station in February 2012. Outside, the temperature hovers around -55 degrees Celsius, wind tearing across the ice plateau at 30 kilometers per hour. Inside the drilling complex, a team of Russian engineers and scientists watches a monitor showing the final meters of progress. For more than 20 years, they have been lowering a specialized thermal drill, a hot water jet system followed by an electromechanical bit, through 4,000 meters of ice. The goal is not just to reach the lake's surface, but to do so cleanly, without letting kerosene-based drilling fluids or surface microbes flood into the pristine water below. As the drill approaches the final barrier, the team switches to a different technique. They insert a probe that melts the last few meters using a combination of heat and mechanical action, while keeping the borehole filled with a non-toxic silicone fluid to prevent collapse. At 3,768 meters depth, the probe suddenly registers a sharp pressure increase. Lake water surges upward into the borehole under its own immense hydrostatic force, proof that the seal has been broken. The rise is controlled. The water climbs about 40 meters up the pipe before equilibrium is reached. Samples are collected immediately from that rising column using sterile syringes and sealed containers designed to maintain high pressure during retrieval. That single connection, lasting only minutes before the borehole was capped, gave science its first direct access to water that had been isolated since the Miocene epoch. The recovered fluid was cold, crystal clear, and carried a subtle mineral taste when tiny test amounts were examined under laboratory conditions. Chemical analysis showed elevated levels of dissolved gases, including the oxygen supersaturation we discussed earlier, along with trace ions consistent with long contact with ancient bedrock. No dramatic gush occurred, no explosive release of trapped methane or sudden destabilization. The system proved stable, just as thermodynamic models had predicted for decades. The engineering challenge had been enormous. Conventional oil drilling fluids would have contaminated the lake irreversibly. Instead, the team developed a multi-stage approach. Kerosene for the upper, colder sections where it remained viscous and non-mixing. Then a switch to cleaner fluids closer to the base. Finally, the thermal probe for the last stretch. Every component was tested for microbial sterility. Air filters, positive pressure in the drill tent, ultraviolet sterilization of tools, all designed to keep surface bacteria from hitching a ride downward. Post-drilling analysis of the samples showed remarkably low levels of modern contaminants, far below what would be expected from less careful operations. Yet the breakthrough sparked immediate debate in the international scientific community. Some researchers argued that any human access carried unacceptable risk of forward contamination, introducing earth microbes that could alter the lake's native biology forever. Others pointed out that the accretion ice already contained microbial signals, and that careful, minimal contact sampling could yield invaluable data without significant harm. The consensus that emerged favored continuing study, but with stricter protocols for future missions. No full-scale penetration without robotic, sealed sampling systems capable of returning pristine water and sediment under pressure. Since that first contact, follow-up efforts have focused on non-invasive methods. Satellite radar, airborne gravimetry, and seismic arrays have mapped the lake floor in greater detail, revealing subtle variations in depth and possible sediment thickness up to 70 meters in places. Heat flow measurements from boreholes nearby suggest a modest geothermal gradient, enough to balance basal melting, but not enough to drive vigorous hydrothermal circulation. These remote observations have refined our understanding without additional physical intrusion. The 2012 event remains a landmark in polar exploration, comparable in spirit to the first deep-sea submersible dives or the Apollo landings, yet quieter and more deliberate. No flags were planted, no live video streamed to the world. Just a small team in an isolated station, listening to instruments, collecting sealed vials, and knowing they had bridged 20 million years of separation in a matter of moments. What makes this achievement resonate so deeply is the restraint involved. The team could have pushed for larger samples or deeper probes. Instead, they prioritized preservation. The lake was treated not as a resource to exploit, but as a scientific treasure, one that might hold clues to life's limits on Earth and beyond. That philosophy guided every decision. Minimize disturbance, maximize data quality, document everything meticulously. Reflect for a second on the human element here. These were not adventure seekers chasing headlines. They were engineers who spent years perfecting drill bits that would not crack under extreme cold. Biologists who cultured control samples for months to prove sterility. Glaciologists who modeled ice behavior to predict how the borehole might close after withdrawal. It was collaboration across borders. Russian leadership, with input from British, American, and French teams, sharing radar data and modeling expertise. The result was not conquest, but a careful handshake with an ancient system. The piercing of the ice opened a narrow window, one that closed quickly and has not been reopened in the same way since. Future plans center on cleaner, robotic technologies. Autonomous probes lowered through boreholes, equipped with sensors and sample collectors that never expose the lake to surface air. Those missions, if funded and executed, could return far more detailed profiles of chemistry, microbiology, and physical conditions without repeating the minimal risks of the first touch. We have witnessed humanity's first respectful intrusion into a world sealed since before our ancestors walked upright. But that single touch revealed more than water chemistry. It brought back traces of life forms so unusual, they seemed to belong to a different branch of biology. Those strange microbial relatives are waiting just ahead. We have witnessed humanity's first respectful intrusion into a world sealed since before our ancestors walked upright. But that single touch revealed more than water chemistry. It brought back traces of life forms so unusual, they seemed to belong to a different branch of biology. Those strange microbial relatives are waiting just ahead. Claiming ninth place, the mysterious microbial kin that share almost no family resemblance with anything living on the sunlit surface. Imagine holding a tiny vial of water pulled from the depths of Lake Vostok. Water that rose under its own pressure after 20 million years of solitude. Under the microscope, you would not see dramatic shapes at first. No wriggling flagella, no intricate colonial structures like you find in pond scum. Instead, faint clusters of cells appear, some rod-shaped, some spherical, others irregular blobs barely a micrometer across. Their membranes look unusually thick and reinforced, as if built to withstand constant high pressure and oxidative stress. When genetic sequencers read their DNA, the results force a double take. These organisms are not close cousins to common soil bacteria or ocean plankton. Their nearest known relatives live in completely different extreme environments. Deep-sea hydrothermal vents, hot springs near volcanoes, or the rocky subsurface hundreds of meters below continental crust. One of the most striking discoveries from the carefully filtered samples and accretionized DNA came in the form of a dominant bacterial group whose closest matches, at only 70 to 80% genetic similarity, belong to lineages found around black smokers on the mid-ocean ridge. Those vent microbes thrive on hydrogen and sulfur compounds in total darkness, using chemical energy instead of sunlight. The Lake Vostok sequences show similar metabolic pathways. Genes for oxidizing trace hydrogen, reducing iron or manganese, and handling sulfur in low concentrations. Yet the match is distant enough that these lake dwellers form their own distinct cluster, a branch that split off long ago and evolved in isolation under radically different conditions. What sets them apart even more is their apparent adaptation to the lake's unique cocktail of extremes. Surface relatives from vents deal with high temperature and low oxygen. Here, the temperature is near freezing, oxygen is overwhelmingly abundant, and nutrients arrive in vanishingly small doses. Genetic analysis reveals expanded gene families for enzymes that detoxify reactive oxygen species, superoxide dismutases, catalases, peroxidases, far more copies than seen in most aerobic bacteria. There are also sequences suggesting novel, cold-adapted proteins that keep cell membranes flexible at -3 degrees Celsius, and antifreeze-like compounds that prevent ice crystal formation inside the cell, even when tiny ice nuclei form nearby. To visualize their lifestyle, picture these cells suspended in near-perfect stillness. Energy comes in trickles, perhaps a molecule of hydrogen diffusing from a slow water-rock reaction in the bedrock, or a bit of dissolved organic carbon carried down in meltwater from the ice sheet above. Each cell might process only a few dozen molecules per hour, enough to repair damage, replicate DNA once every few months, and divide perhaps once a year. It is existence stripped to the bare minimum. No waste, no extravagance, just persistent chemical bookkeeping in a pressurized vault. Some may form biofilms on sediment grains or mineral surfaces, sharing the rare nutrient windfall when a fresh particle settles from the melting ceiling. Others drift freely, waiting for the slow tidal currents to carry them towards slightly richer microzones. The genetic distance is what really captures attention. When scientists build phylogenetic trees, those branching diagrams showing evolutionary relationships, these Lake Vostok sequences often fall outside established bacterial phyla, or sit on long, solitary branches. They are not archaea in the classic sense, nor do they nest neatly within proteobacteria, firmicutes, or any of the major groups that dominate surface ecosystems. Instead, they hint at deep, ancient divergences, lineages that may have originated before the last common ancestor of most known bacteria, then followed a separate evolutionary path sealed beneath the ice. Whether they represent truly novel phyla or highly derived members of known groups remains under active study, with more sequencing and comparative genomics needed to settle the question. This strangeness carries real scientific weight. If these microbes are indigenous, and multiple lines of evidence, including low contamination and clean samples, support that view, they demonstrate that life can diverge dramatically when isolated for geological timespans. On the surface, rapid environmental shifts drive convergence. Similar solutions evolve independently in distant lineages. Here, with no predators, no competition from newcomers, no seasonal changes, evolution has had free rein to explore unusual biochemical space. The result is a set of metabolic tricks and stress response systems that look alien even to experts in extremophile research. Compare this to what we find in other subglacial environments. Smaller Antarctic lakes show microbial communities too, but often with closer ties to surface soils or marine bacteria carried in by ancient connections. Lake Vostok stands out for its deeper isolation and the resulting genetic novelty. It suggests that 20 million years is long enough for significant evolutionary drift, enough to produce organisms that, while still bacteria, feel like visitors from a parallel biosphere. The implications stretch beyond Earth. Astrobiologists frequently cite subglacial lakes as the best terrestrial analogs for the buried oceans of Europa, Enceladus, and other icy moons. If microbes can sustain themselves on geochemical energy in a high-pressure, dark, oxygen-rich pocket beneath kilometers of ice here, similar life could plausibly exist where sunlight never reaches but chemical gradients persist. The unusual genetics from Vostok remind us that we should expect surprises, not Earth-like cyanobacteria or simple heterotrophs, but organisms shaped by conditions we can barely replicate in the lab. Take a moment to absorb that idea. The tiniest inhabitants of this hidden lake may represent one of the most divergent branches of life still active on our planet. Distant relatives not just of vent bacteria, but of everything else we consider familiar. They have lived through ice ages, continental rearrangements, mass extinctions above, all while quietly refining their chemistry in the dark. Their existence alone expands our definition of what a habitable environment can look like. We have encountered microbial strangers that rewrite family trees. But something even deeper fuels their quiet persistence. Heat rising from the planet's interior that keeps the whole system from freezing into oblivion. That hidden warmth is next. We have encountered microbial strangers that rewrite family trees, But something even deeper fuels their quiet persistence. Heat rising from the planet's interior that keeps the whole system from freezing into oblivion. That hidden warmth is next. Stepping into 10th place, the subtle inner glow from deep within Earth that quietly prevents an entire buried lake from turning into solid ice. Imagine standing on the frozen surface of East Antarctica. The wind biting at your face, everything around you locked in temperatures that rarely climb above minus 40 degrees Celsius. Now picture what lies far below. Not just the ice sheet and the dark water of Lake Vostok, but the solid bedrock underneath. And beneath that, the slow, steady pulse of heat escaping from the planet's mantle. This geothermal energy is faint compared to what you feel near volcanoes or hot springs. Yet it is exactly the right amount to tip the balance in this extreme environment. Scientists measure this heat flow in units called milliwatts per square meter. At most places on Earth's continents, the value sits between 40 and 60 milliwatts per square meter. In Antarctica, the numbers are generally lower because the thick ice sheet acts as a powerful insulator, trapping heat and slowing its escape. But beneath Lake Vostok, measurements and models consistently show a slightly higher flux, somewhere between 50 and 100 milliwatts per square meter, sometimes approaching 110 in localized spots. That small extra warmth, delivered continuously over millions of years, is what keeps the lake from freezing solid at the bottom, despite the enormous pressure and near-freezing temperature. To understand why this matters, think about the energy balance at the ice-water interface. The glacier above is slowly sliding across the lake basin at roughly 2 to 3 centimeters per year. As it moves, friction between the ice and the bedrock generates a tiny amount of heat, enough to melt a few millimeters of ice at the base each year. On top of that, the geothermal heat coming up from below adds another small but steady contribution. Together, these two sources exactly balance the heat loss that occurs as colder ice from the surface gradually accretes onto the bottom of the glacier. The result is a near-perfect equilibrium. The lake loses some water to freezing at one end, gains a matching amount from melting at the other, and the water column stays liquid without growing or shrinking significantly over geological time. If that geothermal heat were absent or significantly lower, the bottom would slowly freeze upward, forming thick layers of bottom ice that would eventually fill much of the basin. If the heat were much higher, vigorous melting would thin the ice sheet from below, potentially destabilizing the entire structure. The fact that Lake Vostok has maintained its liquid state for at least 15 million years tells us the geothermal flux has stayed within a very narrow window, probably one of the most stable thermal regimes on the planet. How do researchers actually measure this heat when everything is buried under kilometers of ice? Direct measurements come from temperature profiles recorded in deep boreholes drilled nearby. Thermistors lowered into the ice show how temperature changes with depth. Near the surface, the temperature drops sharply due to the cold air above. Deeper down, the gradient becomes very gentle because the ice is such a good insulator. At the bottom of most boreholes, the temperature rises again, a clear sign that heat is flowing upward from below. By combining these profiles with models of ice thermal conductivity and heat capacity, scientists calculate the flux at the bedrock. Additional evidence comes from airborne and satellite surveys that detect subtle gravity and magnetic anomalies. Warmer bedrock tends to be slightly less dense and can carry different magnetic minerals, creating faint signals that match areas of higher heat flow. Seismic data also help. Sound waves travel differently through warmer, less rigid crust. All these independent methods converge on the same conclusion: a modest but crucial geothermal contribution beneath the lake. Now try to visualize the scene at the lake floor. The bedrock is ancient continental crust, possibly more than 2 billion years old, scarred by earlier tectonic events. Heat escapes through microscopic cracks and grain boundaries, warming the thin sediment layer, perhaps a few tens of centimeters thick, that has accumulated over millions of years. That warmth radiates upward into the water column, creating tiny density differences. Slightly warmer, less dense water near the bottom rises very slowly, while colder water sinks elsewhere. These weak convection cells help distribute heat and dissolved chemicals, preventing stagnation and keeping the lake mixed on extremely long timescales. The geothermal heat also influences the oxygen story we talked about earlier. Higher temperatures increase the solubility of some gases and affect the stability of clathrate structures. In the coldest parts of the lake, small amounts of oxygen may be trapped in cage-like hydrate crystals. In slightly warmer zones near the bottom, those structures become less stable and release their cargo back into solution. The result is a dynamic equilibrium that keeps oxygen levels high everywhere. This faint inner warmth is one of the quietest but most essential characters in the Lake Vostok story. It does not roar like a volcano or bubble like a geyser. It simply persists, a slow leak of planetary energy that has been running steadily since long before humans existed. Without it, the lake would be just another frozen pocket sealed beneath the ice. With it, the system stays alive as a liquid body capable of supporting chemistry and, potentially, life. Reflect for a moment on the scale of this balance. A difference of only a few tens of milliwatts per square meter, less power than a small LED bulb emits per square meter, is all that separates a stable liquid lake from a completely frozen basin. It is a beautiful example of how tiny, sustained inputs can maintain complex systems over geological epochs. We have felt the planet's own warmth rising to protect its hidden water. But that warmth does more than keep things liquid. It creates faint disturbances in the invisible fields that surround us. Those strange signals flickering below are coming up next. We have felt the planet's own warmth rising to protect its hidden water. But that warmth does more than keep things liquid. It creates faint disturbances in the invisible fields that surround us. Those strange signals flickering below are coming up next. Moving into 11th place, the subtle, invisible magnetic ripples that hint at deep twists in the Earth's crust far beneath the ice. Imagine flying low over the East Antarctic Plateau in a research aircraft equipped with sensitive magnetometers. The plane traces tight grid lines across the endless white, instruments recording tiny variations in the planet's magnetic field every few meters. Most of the time, the readings are smooth, following the broad, predictable patterns of Earth's main dipolar field. Then the aircraft passes directly over Lake Vostok. Suddenly, the compass needle, or rather the digital equivalent, twitches. The total magnetic field strength drops by about 1 microtesla over an elliptical patch roughly 105 kilometers long and 75 kilometers wide. That dip is small, less than 1% of the background field, yet it stands out sharply against the surrounding uniformity. This magnetic anomaly has been mapped repeatedly since the late 1990s, using both airborne surveys and satellite missions that measure the geomagnetic field from space. The low spot sits almost exactly centered above the lake basin. It is not random noise or instrument error. Multiple independent datasets, from Russian, British, and American teams, show the same feature, a localized weakening of the magnetic field that aligns perfectly with the outline of the subglacial water body. Why would a buried lake cause such a signal? The explanation lies in the crust beneath it. The magnetic field we measure at the surface is generated mostly by the molten iron outer core, thousands of kilometers down. But the rocks in the upper crust can become magnetized over geological time. When iron-rich minerals like magnetite cool through their Curie temperature in the presence of Earth's field, they lock in that direction, like tiny permanent magnets. Thick continental crust, especially ancient shields like the one under East Antarctica, usually carries strong remnant magnetization, contributing to a relatively high and uniform field. Under Lake Vostok, however, the picture changes. Seismic and gravity data suggest the crust here is thinner than in surrounding regions, perhaps by several kilometers, and possibly fractured or thermally altered during ancient tectonic events. Thinner crust means less magnetized rock volume contributing to the total field. Warmer temperatures from the slightly elevated geothermal flux we discussed earlier could also push parts of the crust closer to the Curie point, reducing remnant magnetism further. The combined effect creates a magnetic low. The field lines dip downward slightly, as if the underlying rock is pulling less strongly on the planetary field. To visualize this, think of the Earth's magnetic field as a set of invisible rubber bands stretched from pole to pole. Over most of the continent, those bands run smoothly. Above the lake, they encounter a region where the anchor points in the crust are weaker or missing. The bands sag a little, creating a subtle dent in the field strength measured at the surface and from satellites. The anomaly is elongated along the lake's long axis, mirroring the basin shape almost exactly. One of the cleanest geological matches between a surface geophysical signal and a subglacial feature ever observed. This magnetic signature carries deeper implications. A thinned or altered crust often indicates past tectonic activity, perhaps an ancient rift or shear zone that helped shape the East Antarctic Shield billions of years ago. The presence of such a structure beneath the lake could explain why this particular bedrock depression became deep enough to trap water when the ice sheet advanced. It might also influence how heat escapes from below, channeling geothermal flux along fractures and keeping the basal melting balanced. From a broader perspective, the anomaly reminds us that even the most remote, ice-covered parts of the planet still bear the scars of deep geological history. The crust under Antarctica is not uniform granite slab. It is a mosaic of old terrains, suture zones, and thermal anomalies, many of them hidden until geophysical tools revealed them. Lake Vostok sits right on one of those hidden boundaries, where the magnetic field quietly betrays the presence of something unusual far below the ice. Scientists use these magnetic data in sophisticated inversions, computer models that try to reconstruct the subsurface magnetization distribution needed to produce the observed surface signal. The best-fitting models consistently show reduced magnetization directly beneath the lake, with the anomaly source located within the upper 10 to 15 kilometers of crust. Independent gravity surveys show a corresponding low-density zone, reinforcing the idea of thinner or less dense crust. Together, the datasets paint a consistent portrait of a structurally distinct region cradling the lake. The faint magnetic flicker also has practical value. It helps refine maps of subglacial topography and hydrology. Because the anomaly is so sharply defined, it serves as a natural marker for tracking the lake's outline in places where radar echoes are ambiguous due to steep bedrock slopes or thick sediment. Future airborne campaigns will likely fly even tighter lines over the feature to resolve finer details, perhaps detecting smaller offsets that could indicate active faulting or fluid pathways. Reflect on the quiet power of this discovery for a moment. We are talking about a change of 1 microtesla, a variation so tiny that a handheld compass would barely notice it. Yet it reveals a geological story stretching back billions of years. It shows how interconnected Earth systems really are. Ancient continental collisions leave magnetic fingerprints that we can still read through 4 kilometers of ice. And those fingerprints help explain why a lake this size and this old could exist at all. The magnetic low is one more layer of strangeness in a place already full of them. It tells us the crust beneath is not passive bedrock, but an active participant in the lake's long history. Thinned, perhaps fractured, quietly influencing heat, magnetism, and stability from below. We have traced the invisible magnetic dent that marks a deeper crustal twist. But that twist is not just an earthbound curiosity. It turns Lake Vostok into one of our best stand-ins for entire oceans hidden beneath the ice of distant moons. That cosmic parallel is next. We have traced the invisible magnetic dent that marks a deeper crustal twist. But that twist is not just an earthbound curiosity. It turns Lake Vostok into one of our best stand-ins for entire oceans hidden beneath the ice of distant moons. That cosmic parallel is next. Earning 12th place, the frozen mirror that lets us glimpse what alien oceans might really be like right here on our own planet. Picture this. You are an astrobiologist, standing in a clean room at a major research institute, looking at the latest high-resolution radar maps of Europa, one of Jupiter's icy moons. The surface is cracked and ridged like a giant frozen eggshell. Beneath that shell, models predict a global ocean of liquid water, possibly 100 kilometers deep, trapped under 10 to 30 kilometers of ice. No sunlight reaches that depth. No rivers feed it. No air touches its surface. The only energy sources are tidal heating from Jupiter's gravitational pull and perhaps some geothermal flux from the Moon's rocky core. Sound familiar? Now shift your gaze to the radar image beside it, Lake Vostok. The same basic architecture stares back, a deep basin of liquid water completely enclosed by thick ice, cut off from sunlight, sustained by pressure, slow tidal flexing, and faint heat from below. The parallels are so close that NASA, the European Space Agency, and teams studying future missions to Europa and Enceladus routinely list subglacial Antarctic lakes, especially Vostok, as the most realistic terrestrial analogs we have for those extraterrestrial oceans. Why is the match so strong? Start with isolation. Europa's ocean has likely been sealed beneath ice for billions of years. Lake Vostok has been sealed for 15 to 25 million years. Not as long, but long enough to create a near-pristine, low-energy environment where surface contamination is minimal and evolutionary pressures are extreme. Both systems rely on pressure to keep water liquid at sub-zero temperatures. Both experience tidal deformation. On Europa, the tides are massive, raising and lowering the ice shell by tens of meters twice per orbit. On Vostok, the effect is tiny, just 12 millimeters, but the physics is identical. Gravitational flexing transmitted through solid ice to a liquid interior. Then there is the energy budget. On icy moons, the dominant power source is tidal dissipation, friction inside the moon as it is stretched and squeezed. That heat keeps cracks open, allows chemical reactions at the rock-water interface, and potentially drives hydrothermal vents on the sea floor. In Lake Vostok, the tidal flex is minuscule, but geothermal heat from the crust plays a similar role. It melts basal ice at a steady rate, maintains circulation, and supplies trace chemicals that microbes could use. In both cases, life, if it exists, must run on chemosynthesis, not photosynthesis. Hydrogen, iron, sulfur compounds, maybe methane, all become potential fuel in darkness. The oxygen story adds another layer of similarity. Recent models for Europa suggest its ocean could be oxygen-rich because radiation from Jupiter splits water molecules at the surface, and the resulting oxygen slowly diffuses downward through the ice over geological time. Lake Vostok shows exactly what ultra-high dissolved oxygen looks like in a sealed, cold, high-pressure system. Concentrations up to 50 times surface levels. If Europa's ocean carries similar oxygen from radiolytic production, the chemistry could support aerobic metabolism even without sunlight, mirroring what we infer from Vostok's gas data. Microbial life provides the most tantalizing link. The unusual vent-like bacterial sequences recovered from Vostok accretion ice look strikingly similar to organisms found around deep-sea hydrothermal vents on Earth. The very ecosystems astrobiologists use as templates for possible life in icy moon oceans. Genes for hydrogen oxidation, iron reduction, and cold stress resistance appear in both settings. If those Vostok microbes are truly native, they demonstrate that chemolithotrophic communities can persist indefinitely in dark, pressurized, nutrient-poor water. Precisely the conditions expected beneath Europa's or Enceladus's ice shells. Of course, the differences matter too. Europa's ocean is vastly deeper and likely saltier, with stronger tides and possible seafloor volcanism. Enceladus has active plumes shooting water into space, giving us direct samples of its ocean chemistry. Vostok is smaller, fresher, and geothermally quieter. Yet those differences make the lake even more valuable. It fills in the spectrum of possible sub-ice environments. Not every hidden ocean needs vigorous hydrothermal vents or massive tides. A modest, stable heat flow and slow circulation, like Vostok, could be enough to sustain life for eons. This analog role shapes real mission planning. When the European JUICE spacecraft launches toward Jupiter, or when NASA's Europa Clipper flies past the Moon, Scientists will compare its radar returns, magnetic field perturbations, and plume chemistry to what we see at Vostok. If JUICE detects a sub-ice lake on Ganymede or a faint magnetic anomaly over Europa, the first place teams will look for interpretation is the Antarctic Data Archive. Vostok has become the benchmark, the place where we test instruments, train sampling protocols, and refine models before sending hardware billions of kilometers away. Think about the quiet poetry of that connection. A lake buried under Antarctic ice, untouched since before our species existed, now serves as Earth's best proxy for oceans orbiting a gas giant 400 million miles from the Sun. It reminds us that the most extreme environments on our planet often hold the clearest clues to what might exist beyond it. Every radar profile of Vostok, every microbial sequence, every heat flow measurement is not just local science. It is rehearsal for questions we hope to answer on other worlds. The lake does not just mirror distant oceans in structure, it mirrors them in possibility. If life can hang on in this pressurized, oxygen-saturated darkness, even if only as sparse, slow-growing cells, then the odds improve that similar life could hang on beneath Europa's cracked shell or Enceladus's geyser plumes. Vostok does not prove alien life exists. It proves that the physical conditions needed for it to exist are not as exotic as we once thought. We have looked through Earth's clearest window into alien seas, but that window also looks outward in time. The sediments and ice layers beneath and above the lake preserve records of ancient climates that could reshape how we understand global change right here at home. Those echoes in the currents of our own planet are the final revelation. We have looked through Earth's clearest window into alien seas. But that window also looks outward in time. The sediments and ice layers beneath and above the lake preserve records of ancient climates that could reshape how we understand global change right here at home. Those echoes in the currents of our own planet are the final revelation. Reaching the peak at 13th place, the deep time archive locked in sediment and ice that quietly warns us about the future of our own world. Imagine you could somehow walk along the floor of Lake Vostok right now. No light reaches you. The water presses from every side. Beneath your feet stretches a layer of fine silt and clay, perhaps up to 70 meters thick in the deepest parts of the basin. That sediment did not arrive quickly. It settled at an excruciatingly slow rate, roughly 1 to 2 millimeters every 1,000 years. Over 15 to 25 million years, those thin layers have stacked into a continuous record of dust, volcanic ash, cosmic particles, and chemical traces, carried down from the melting ice ceiling above. This is one of the slowest depositing environments known on Earth, slower even than the deep ocean floor in many places. Every particle tells a story. Winds that blew across distant continents millions of years ago lifted microscopic dust and dropped it onto the Antarctic plateau. That dust fell with snow, became part of the ice sheet, slowly migrated downward as the glacier flowed, and eventually melted out at the base, settling into the lake. Volcanic eruptions from Patagonia, New Zealand, or even farther afield sent ash particles that traveled thousands of kilometers through the stratosphere before landing here. Cosmic dust from passing comets and asteroid collisions sprinkled iridium and other rare elements. All of it accumulated in neat, undisturbed layers, preserved by the cold, the darkness, and the lack of burrowing organisms or strong currents to mix things up. Above the sediment, the overlying ice sheet itself holds an even more detailed diary. Ice cores drilled just outside the lake basin, some reaching back more than 800,000 years, contain trapped air bubbles, isotopic ratios in the ice crystals, and microscopic inclusions that record past temperatures, atmospheric carbon dioxide and methane levels, solar activity, and major volcanic events. Because the ice flows slowly over the lake, the bottom layers have been accreting lake water for millions of years, creating bands of frozen lake water called accretion ice. Those bands carry dissolved gases, salts, and microbial traces directly from the lake itself, bridging the sediment record below with the atmospheric record above. Together, these archives form one of the most complete long-term climate libraries we have. The sediment core, though never fully sampled due to contamination concerns, has been imaged with seismic reflection and inferred from gravity and magnetic data. It shows rhythmic variations in thickness and composition that match known cycles of Earth's orbit. The eccentricity, tilt, and precession that drive ice ages over tens to hundreds of thousands of years. Deeper layers likely capture even older transitions, the shift from a warmer, greener Antarctica 34 million years ago to the permanent ice sheet we know today. If we could read those layers in detail, they would reveal how the planet crossed tipping points, when carbon dioxide dropped below critical thresholds, when ocean currents rearranged, when ice began to spread irreversibly. The lake's role as a climate sentinel becomes sharper when we consider modern changes. Satellite measurements show parts of the Antarctic ice sheet losing mass faster than models once predicted, with warm ocean water reaching beneath floating ice shelves and accelerating melt from below. Subglacial hydrology. The network of hidden rivers and lakes like Vostok influences how quickly that meltwater drains to the sea and raises global levels. If warming reaches the East Antarctic interior and begins to thin the ice over these lakes, the delicate balance of basal melting and refreezing could shift. More meltwater entering the lake might dilute its extreme chemistry. Faster ice flow could disrupt sediment layers. In extreme scenarios, parts of the system could become unstable, releasing stored water and affecting larger ice dynamics. Scientists use Vostok as a natural laboratory to test these possibilities. Numerical models of subglacial water flow incorporate the lake's geometry, geothermal heat, and tidal effects to simulate what happens under different warming scenarios. The results suggest the system is surprisingly resilient on human timescales. The thick ice and high pressure buffer against rapid change. But they also highlight vulnerabilities. A sustained increase in basal melt could eventually connect Vostok to other subglacial lakes through hidden channels, creating a larger, interconnected drainage network beneath the continent. That network already exists in West Antarctica. Its expansion eastward would accelerate ice loss in ways current global forecasts do not fully capture. The sediment and ice records also carry lessons about tipping points in the past. During the last interglacial period, about 125,000 years ago, global temperatures were only 1 to 2 degrees warmer than today. Yet sea levels stood 6 to 9 meters higher. Some of that extra water likely came from partial retreat of the East Antarctic margin. If similar warmth returns, the hidden lakes and their drainage pathways could play a key role in how much and how fast ice is lost. Understanding Vostok's long-term stability helps refine those predictions, giving us better maps of where future sea level rise might accelerate. This final wonder is perhaps the most sobering. While the lake captivates us with its isolation, its extreme chemistry, its potential for novel life, and its mirror to alien oceans, it also holds up a quiet mirror to our own future. The same slow, patient processes that preserved its secrets for millions of years now record the fingerprints of a changing climate. Every dust grain, every isotopic shift, every trapped bubble is evidence that Earth's systems remember. And that memory can guide us if we listen closely. The lake does not shout warnings. It whispers through data. Subtle changes in heat flow, faint shifts in magnetic signals, slow accumulation of sediment, gradual accretion of ice. Those whispers accumulate into knowledge that shapes how we prepare for a warmer world. They remind us that even the most remote, seemingly unchanging places are connected to everything else. To past climates, to future coastlines, to the thin habitable zone we call home. We have journeyed through 13 revelations, each one peeling back another layer of a world hidden beneath eternal ice. From colossal scale to ancient isolation, from tidal heartbeats to crushing pressure, from oxygen floods to microbial strangers, from careful human touch to magnetic whispers and cosmic mirrors. Lake Vostok has shown us how much wonder and warning can hide in plain sight. Now you hold all 13 secrets, from the giant basin cradled under 4 kilometers of ice to the deep time warnings locked in its sediments. This buried world has rewritten what we thought we knew about isolation, resilience, and the thin line between frozen and fluid. Now you understand why a single subglacial lake can teach us about Earth's past, its present stability, and the possibilities waiting in oceans orbiting distant stars. Which of these wonders surprised you the most? Drop it in the comments below. I read every one. Cherish these hidden corners of our planet. Stay curious, keep exploring, and I'll see you in the next deep dive.